Okay, so we're going to switch to the FluMapper, which I think is a really cool application.
Thank you, Mary. And I guess
Yeah,
stay here.
let's
Okay.
do our best.
Let's see. So given the time, I think we have 3 presentations in this session. So we talked about the toolkit and we had the gateway, and now we are coming to the 3rd session, which is the middleware, which is the middle portion, which bridges between the high-end supercomputing environment, the toolkit, and the gateway. So we are going to use FluMapper, which has been integrated into a gateway, as a driving example for explaining what are the capabilities being provided by the middleware. And so since we have around 35 minutes for this whole session, so I was planning to do a 25 minutes presentation, but I will cut it down to around 15 to 20 minutes presentation. Okay, so let's see if I can make it full screen. So can I see it? Yeah, okay. Okay, thank you. So this is kind of a collaborative work led by the University of Illinois, and we are going to use FluMapper as one of our application drivers to show how to do interactive spatial analysis on streaming social media data and how the middleware is supporting this application. So motivations for this FluMapper application as such, we have conventional approach to disease surveillance, which are usually physician data or hospital visits. These are typically updated weekly or at a specific spatial scale, typically a region, which is for the CDC, or at state or city level, which Google does. And we have noticed that various studies have shown that social media data has capability of giving us valuable information for problems which have significant social impact, like stock market prediction, which was a very famous paper, and even infectious disease modeling and disaster responses. So, and with the large volume of data which is coming in from these social media kind of channels, this is a perfect bridge to something which, a problem which cannot be done without CyberGIS capabilities. So advantages of using the location-based social media data, it's obviously rich in both space and time. We have quite a bit of themes also which could be gleaned from these kinds of data. These are very efficient to collect. The data is very cost-effective rather than surveys or clinical data. Those are quite expensive to generate, and these can be collected in almost near real time using APIs and stuff like that. And at core, they provide individual observation, and their use is far less restrictive than traditional data. However, there are challenges in terms of the data size can be quite large, and the data itself is unstructured, so it's difficult to say what exactly is this particular tweet or this post talking about. It's in a particular context. So that's kind of a challenge, more of a natural language processing, those kinds of challenges, and how to interpret what is being said in the social media space. And then obviously there is a statistical sampling. So the goals of this FluMapper was to create an exploratory tool to do an interactive analysis on this social media data to provide public health practitioners some way to detect flu as indicated by this data set, and efficiently manage this large volumes of data coming in. And we are doing it across multiple space time scales. So we are able to give at very fine spatial scale to very coarse spatial scale. We are doing 2 kinds of analysis for this, like the exploratory data analysis as well as the movement patterns, because we have very fine level GPS kind of data coming in from social media. So in the context of the CyberGIS software ecosystem, we have the gateway, we have the toolkit, which we have talked about, and we have the GIS middleware, which is bridging in this gateway and toolkit. In this example, what we have is we have the FluMapper, which provides a web end which is on the gateway. You can go to the gateway, the sandbox gateway, which looked demoed for the CG PySal, as well as Mary showed for her integration. If you can go there, you will see FluMapper as listed as an application there. So the architecture, so coming back to the middleware portion of it, in order to support this FluMapper application, this is kind of the architecture. We are using Twitter data in this case. We are collecting the data, and we are recording it in massive databases in the backend, and we are using our GISOL Open Service API in order to do the analysis. I'll go into a little bit more detail on this architecture in the following slides. So the components, two major things. We have the data handling component for the big streaming social media data coming in, and we have the spatial analysis components. For data handling, collecting, and processing, we are doing it. We are getting near real-time data from Twitter using their streaming API, and they are being processed and transformed into something which could be understood by the later steps. And we have a spatiotemporal data model, which is basically a space-time cube, which is there to support effective and quick processing query. At this stage, we are doing the whole North America data. At the finest level, it's done at 30 arc seconds. And the spatial data analysis, we are doing two kinds of spatial data analysis: exploratory spatial data analysis, which uses kernel density estimation, and we are doing a flow mapping kind of analysis using this data to see the movement pattern of the users from this massive data. So I talked about this in terms of providing near. So for data handling, we are using the Twitter streaming API to get this data near real time. We are using techniques like support vector machines and keyword filtering in order to identify, in this particular case, flu-related keywords and tweets. And then for the analysis, at present, we are using a 7-day sliding window to do an interactive analysis. So the GISOL middleware was extended in order to interact with now the MongoDB. This is a scalable, distributed scalable open source NoSQL database, and this right now stores both the tweet information as well as the spatial temporal data cubes. This is the architecture for data handling. We have the crawler, which is collecting data constantly from Twitter using the streaming API. We just specify the North America as a bounding box, so we are getting all the tweets in North America, either flu-related or non-flu-related, and then we are storing it in a cache. And then we have an importer module in order to transform, in order to apply the support vector machine and transform these and identify flu-related keywords and flu-related tweets. And we have a cube generator module which generates this space-time cube. Lastly, we have this filter, which actually provides an efficient and scalable way to query this MongoDB database. Without repeating myself, like the crawler, we are getting around 2.5 million tweets a day. This is being constantly collected, and we have been collecting almost for a year now. And we are using, and for the cube, we have at North America, we have a 1 kilometer by 1 kilometer kind of a grid resolution for the whole North America. And the cube right now stores information regarding the statistics associated with the region, how many flu tweets were there in the region, how many flows, meaning like say how many people moved from one region to the other, what is the interdependency between one portion of the cube to the other. So it's a space-time cube, so between each pair of these cuboids, what is the movements, basically for collecting statistics. So this is the data part. Now we have the analysis part. As I said, we have two analysis, the flow mapping analysis and the exploratory spatial data analysis using kernel density estimation. The flow mapping analysis, we have basically two kind of techniques. We have a single source and an all source, which we call move pattern, in order to do a scalable interactive visualization of move patterns. We have more details on, on the 2 posters. We have 2 student posters, and you're welcome to come and talk to our students who implemented many of these methods this evening. We are using Hadoop-based strategy in order to process this large, massive scale data in order to get these flows, and we have effective scalable query mechanism implemented in GISolve. So let's see. So this is the architecture of the middleware, the backend architecture which was used for move pattern. So you have the web interface, the FluMapper web interface, which I will demo shortly, and we have a servlet in the backend, a Java-based servlet, which is deployed under Tomcat, which basically communicates with the web engine, web frontend. And in the backend, we have all the details of the computation, which is being done in the what's called the data summarization unit, which is the Hadoop portion of the code, which processes and creates this graph, which if you will see that it goes from a very complex graph, because you have all flows of all the people, so it's very dense, and so you cannot really make any sense out of it. But then you are doing data summarization, you're doing visualization on it, so that you're transforming the graph into something which can be easily visualized, and it makes actually sense for it to be presented to the user. And the mapping is actually done on real-time basis, on request. So when you're moving the window, so your new window is being passed to the servlet, and then the map is based on your new window. So the second analysis we are doing is the exploratory spatial data analysis, which uses kernel density estimation. It also uses Monte Carlo based random labeling. We had Dr. Shi talk this morning about his method on using RCMC and UCMC. This is using a similar technique in order to do a risk estimation on the surface using the Twitter data. And we are generating, in this case, the tweets which indicate flu are used as the case population, and all the tweets form the background population. The code for this has been implemented in GPU using CUDA, the programming language, and it's been executed on one of the Exceed supercomputers. And in order to do that, we are using the GISolve open service API in order to invoke and execute this. So, to the demo part. So you can all go to flumapper.org. That let's see if that actually. So you can go ahead to, you don't need to remember that complex URL, just go to flumapper.org and you can see that. So you see this interface here, you have a setting panel, and then, so when you click on a point, so this is a route based, so you're seeing an interactive visualization of how many people are moving. This is all population, you can see flu only kind of risk populations. So based on the data, based on Twitter data, what is the movement we have?
Is that live Twitter data? Is that updated all the time?
This is updated all the time. This map was generated at 10 a.m. And so this morning. So it currently is running every 2-hour kind of cycles. So we are constantly getting data from Twitter, and every 2 hours we are generating the map. The map is generated for a 7-day sliding window. And then we have this play thing, which we record for roughly 1 day based on this data. So the
networks and the flows?
What's that?
Could you explain the networks and the flows?
The networks are road networks at this stage. These are road networks which we deployed a service.
Most people with flu tend to drive.
Right. Well, it depends. It depends on the data. So based on the data, if we see the speed from where you are tweeting to the next tweet. It's not. I know it's not a 100% accurate measure, but it's kind of a measure which tells you whether you travel by road or travel by air.
So if you tweet here,
One day later, or 12 hours later, we have a threshold. You are in Champaign-Urbana, and then we drop those as flows beyond the road network. And the Anand will show you
Right.
M2M
Right.
mapping. Click on the left,
Right.
that could capture air flows.
Right.
So for this flow.
And this also captures, we have air flows also being
Yeah,
captured. So
airflow.
based on the data, roughly estimated speed, and there is a cutoff threshold, and based on that, we estimate whether it's a ground or an air flow.
So the travel on the road network is currently using a routing service.
Routing service.
To map to road network.
So this is somebody who successively tweets about and mentions flu.
Yeah.
Right?
Yeah.
Flew in one of those tweets in the past 7 days, kind of
One of them. And then moves somewhere else and tweets. But the
tweets.
second tweet does not have to mention flu.
Does not have to mention flu.
And why is that evidence that the person has flu?
There's active study in the literature about the keywords selected associated with the possibility of the people having flu based on the retweets or the keywords mentioned in particular set of Twitter streams. So we could only take advantage of the published work, and then we also have, support of vector machine and classifiers involved in this process. But I think the question is really about the confidence and uncertainty involved, whether you could, make a claim whether a set of tweeters are flu cases. In that regard, what we could make in terms of the safe claims is that this is the tweeter population, based on what they tweet, and it probably gives some confidence estimation there, indicating how much risk there. But we cannot say this is the general population, because Twitter population, of course, even have.
And the logical connection between that and the risk seems a little.
Yeah,
So-
tough problem.
Right. So it's just two analysis kind of overlaid, like.
And your risk has no units. What would be the units of risk?
This is kind of based on the percentage. It's just a kernel density estimation at this stage.
So it's
Relative risk.
metric is number of cases per square something?
Transforms to that, right? If you apply the kernel density estimation, it's kind of a percentage relative risk between the flu and the overall population as indicated by Twitter as all tweets as the background population.
So Twitter raw population versus those tweeters tweeted about the flu keywords. We could get offline.
Right. And the other thing is like, so the other important thing is it's as you zoom in, you're getting a different analysis results, right? So at every level you have a different analysis. So this is a multi-scale kind of an analysis.
This is scale sensitive.
Sensitive.
Once you go into different scales, data aggregated.
Right, at a different. So at the US scale, you are seeing like cell sizes which are quite large. And at the lowest scale, it's like 1 kilometer by 1 kilometer kind of scale. So presumably when you zoom into a particular region, you are able to see what are the variations within the region rather than just seeing the overall. Yes.
So you're reading from the Twitter fire hose, right?
Not the fire hose, but the streaming API.
Okay. And so what kind of, so you said it was 2.4%, how much are you getting?
So I think we are getting 1% of the whole data. That's what it's Twitter limits us to for the whole North America region.
Oh, okay, so you're getting 1%. Of those, about 2% can be geocoded? Since we are requesting geocoded data, like a significant percent of that is geocoded. 2 to 4% of the whole Twitter data is geocoded, but the thing we are getting, a significant percent of them is geocoded. Do you know, like,
50?
Meaning the percentage?
Yeah.
I think it's around 50 to 60% of what we are getting.
And
Is
geocoding as in lat long?
lat long or a place mention. Depends on. Quite a few have lat longs, but some of them just have a place mentioned in them.
So you're combining both.
Right, at this stage, yes.
Do we know why there's a north-south line through North Dakota? Is that some sort of
Yeah, that's the, yeah. that is
heavenly
a-
transition that suddenly?
Right,
the
that's
roots are
an
restored?
artifact, yes, that's an
Or
artifact
what's
of,
it an artifact?
of the analysis, like of the cutoff bandwidth of the, or the cutoff thing we had. Yeah.
So means you geocoded 50 or 6%? You geocoded your Twitter data.
Yes, 50 or 60% of the data we are receiving.
You mean the Twitter, the users, they turn on the GPS or telecom data, or just based on the text, they say what city they are?
Based on, even without like geocoding text data, even what Twitter provides. So Twitter gives us a geocoded tag, either it's a lat long or a place. I don't know the difference, like the percentages between lat long and place, but totally it's around 50 to 60%. Quite a few are GPS, I think, but there are some place informations as well.
So currently, let me make clarification. Currently, we're not arguing that this is able to predict flu risk.
Right.
Currently, we're hypothesizing
Yeah.
that maybe this is a way to do early detection of flu outbreak, because it both tracks
Mhm.
the general trend as well as individual movement
Right.
aggregated at different levels. As you probably know, Twitter data, when it was argued to be able to predict the stock market flow, it took a lot of effort to justify that, because this is not the data collected for the purpose we have.
Right.
And the hypothesis is whether we're able to do this based on the data not collected for the purpose for what we're doing. I think this exercise shows the technical feasibility of this workflow being assembled, and also it tackles the problem of modified area unit problem.
Right.
Interactive user interface allows at multiple levels to see the scale dependence and computed simultaneously, and the data organized automatically. But at the moment, we're not at the level to be able to scientifically justify whether we could only scientifically hypothesize whether we are able to approach this question.
Right.
And in fact, there's hot debate in terms of using keywords in the disease surveillance community. How to do this kind of detection.
Yeah. Let's see, there is one more question.
Have you tried running this at sort of known times, like the start of the college school year, where you can, it's pretty solidly known that you're going to get some interesting patterns?
Right, so we have been collecting the data and we have run the analysis. We are, for the web interface, we are definitely running it every 2 hours, as I said. But we have the data going back, so we can go back and run it at any time. And one thing I want to mention, this is like, okay, flu has been taken as a use case for this, but this is broadly applicable to other. So the context is we have set up this middleware pipeline in order to process this social media data, streaming social media data. It could be applied to flu. We have shown it as a use case applied to flu, but there might be other things like disaster response, which could be applied to. I know my time is up and Tim has been pointing me to this, but I just wanted to let you know that this is the kind of the architecture of the middleware, and we have GIS all open service APIs. There are 2 links there, which gives you the API itself as well as the user guides for using the APIs, and we'll go from there. Concluding remarks, I guess.